Um, Imagine waking up tomorrow and finding out that, like, 70% of the universe, a force taught in literally every astrophysics class on Earth as dark energy, was actually just a massive mathematical typo.
Right, just a colossal rounding error.
Yeah. I mean, usually when we talk about mapping the cosmos, there's this underlying expectation of eventual simplicity for you. We like the idea that if you step back far enough, the chaos resolves into something smooth.
Exactly, something manageable.
But what if it doesn't? What if the universe just refuses to be simple?
Well, that is exactly the precipice that modern theoretical cosmology is standing on right now. We are looking at a mathematical and observational landscape that is fiercely resisting our attempts to smooth it out.
It's totally wild to think about.
It is. I mean, it is the absolute definition of a cosmic scale structural crisis.
Welcome to the deep dive. We are so glad you are here with us today. Okay, so let's unpack this. Today we are exploring a really massive stack of groundbreaking theoretical physics papers, along with some paradigm-shifting research excerpts.
And these papers detail exactly what happens if the cosmological principle is just plain wrong.
Exactly. Our mission here is to thoroughly explore a proposed cosmological framework where the universe doesn't smooth out on large scales. And honestly, the stakes are astronomically high.
Oh, absolutely. Because if these theories hold up, it could erase dark energy from existence entirely.
Which blows my mind. But to understand why this is so revolutionary, we first need to establish our baseline for you. What exactly is the cosmological principle?
So, to put it precisely, it's the fundamental assumption that on sufficiently large scales, the universe is both homogeneous and isotropic.
And homogeneous means it's statistically the same everywhere, right?
And isotropic means it looks the same in all directions. It's basically the ultimate zoomed-out view.
Okay, so it's the bedrock of the Big Bang model and what we call the lambda CDM standard model.
Yes, where lambda stands for dark energy and CDM stands for cold dark matter.
So when cosmologists run the equations of general relativity to understand the expansion of the universe, they aren't like calculating the gravitational pull of every single star and galaxy.
Oh no, that would be computationally impossible.
Right.
Even with today's supercomputers.
Right. Instead, they rely on this principle to treat the universe as a smooth, uniform fluid.
Exactly. This assumption allows for the use of the Friedmann-Lemaitre-Robertson-Walker metric, or, we usually just call it the FLRW metric.
FLRW, got it.
It is the exact mathematical description of a perfectly smooth isotropic universe. It's the framework that gives us a single, clean narrative of cosmic evolution.
It gives us a universe that behaves predictably. But here's the teaser for you. What if upcoming data from massive telescope surveys, next-generation projects like Euclid or the Rubin Observatory, prove that the universe is persistently lumpy?
Well, if it never actually smooths out, it won't destroy general relativity. Einstein is still totally safe.
Phew, okay. Einstein is safe.
Yeah, but it will force a scientific revolution on par with the historic shift from classical thermodynamics to statistical mechanics.
Wow. So we'd have to rethink literally everything we thought we knew about the universe's age, its expansion, and its fate.
We really would. And what's fascinating here is that this assumption of smoothness has been so extraordinarily successful for the past century that it's often mistaken for a proven observation.
Wait, so people forget it's an assumption?
All the time. I mean, the FLRW metric works so perfectly for the early universe, which genuinely was a hot, dense, highly uniform plasma that we just sort of carried the assumption forward to the present day.
So we just assumed that the cosmic structures we see today are just minor perturbations, like tiny ripples on an otherwise perfectly smooth pond.
Right, exactly. But the reality is, the observable universe we live in today is anything but a smooth pond.
Yeah, when we actually look out there with telescopes, we don't see a uniform fluid at all.
Not even close. We see galaxies clustering together into these massive filaments and vast sprawling sheets.
We see superclusters, and crucially, we see incredibly huge empty voids. It looks like a giant interconnected cosmic web.
It really does.
Yeah, it makes me think about trying to model the global climate of the Earth.
Oh, that's an interesting comparison. How do you mean?
Well, imagine trying to predict global weather systems, ocean currents, and atmospheric pressures, but you start by assuming the Earth is completely featureless.
I see where you're going with this.
Like, you just assume the planet is a perfectly flat sphere, covered in exactly 1 inch of water everywhere. No Himalayas, no Mariana Trench, no continents at all.
Right, the math would be incredibly easy to solve on a flat, featureless sphere.
Exactly. But your weather predictions are going to be completely wrong because the mountains and the oceans actually dictate how the fluid moves in reality.
That is a phenomenal analogy, and current cosmology essentially does this. It assumes that if you zoom out far enough, the cosmic mountains and valleys perfectly cancel each other out.
Like looking at a sponge, maybe.
Yeah, a sponge is perfect. Up close, a sponge is full of chaotic holes and dense spots. But current models assume that if you zoom out to a scale of, say, 100 to 300 megaparsecs, the sponge looks completely solid and uniform.
Okay. For you listening, a single megaparsec is over 3 million light years across. So 300 megaparsecs is nearly a billion light years.
Right, and the standard model relies on what is called the end of greatness. It's this hypothesized scale where the universe finally stops being lumpy and becomes statistically homogeneous.
The assumption is that once your sample size is a billion light years wide, the density of matter inside that volume perfectly matches the average density of the whole universe.
But the vulnerability lies right there.
Yeah.
Because the question the physics community is grappling with isn't whether the universe is lumpy up close. We know it is.
Yeah, if you look through a telescope right now, you see the sponge.
Exactly. The profound question is whether that end of greatness ever actually arrives.
What if, even at massive, mind-boggling scales of 1 to 5 gigaparsecs, literally billions upon billions of light years across the universe, remains measurably, persistently lumpy?
And this is where the observations are starting to make theorists very, very nervous. We are finding structures that simply shouldn't exist if the end of greatness is real.
Like what kind of structures?
Well, for example, we found things like the Hercules Corona Borealis Great Wall. It's a massive superstructure of galaxies that is roughly 3 gigaparsecs across.
Wait, 3 gigaparsecs? But if the universe is supposed to smooth out at 300 megaparsecs, how do you explain a dense structure that is 10 times that size?
You really can't. It fundamentally breaks the statistical assumption of the FLRW metric.
Which means every single major claim humanity makes about the cosmos, how old it is, how fast it's expanding, is built on an assumption that might be demonstrably false.
Unfortunately, yes. If the universe is a permanent sponge, if it never turns into that perfectly uniform fluid, then our entire cosmic map is completely broken.
So, to understand exactly why it breaks, we have to look deeply at the mathematics. Specifically, we need to talk about Einstein's field equations of general relativity.
Right. These are the equations that describe how matter and energy warp spacetime, which generates what we perceive as gravity. And the absolute most critical detail about these equations is that they are highly nonlinear.
Okay, let's unpack nonlinearity for a second, because that is where the headache really starts for the standard model.
It absolutely is. So in a linear system, the whole is exactly equal to the sum of its parts. If you have two waves in a linear medium, they just pass through each other and add up perfectly.
Simple enough.
But in a nonlinear system, the interactions between the parts generate entirely new, complex effects.
Yeah.
The energy of the gravitational field itself actually gravitates.
Okay, my brain is already twisting.
I know, it's intense. But this creates a massive mathematical paradox for cosmologists when they try to average out the universe.
Because the equations are nonlinear, mathematically averaging the matter distribution of the universe before solving the equations is not the same thing.
Exactly. It is not the same as solving the equations first for the complex, lumpy geometry and then averaging the resulting metric.
Wait, hold on. You're saying we've been doing the math backward this whole time?
In a sense, yes.
That sounds like a colossal oversight for the smartest people on the planet. Are you telling me astrophysicists just decided to average the raw ingredients, plug them into the equations, and assume it gives the exact same result?
Oh.
It's like baking a cake. We've been averaging the raw ingredients together, baking the cake, and assuming it gives us the same result as baking the individual ingredients first and then averaging the cakes.
That's a great way to put it. But it wasn't an oversight born of ignorance, I promise. It was a compromise born of absolute computational necessity.
Okay, fair enough. Defend the physicists.
Well, you have to remember the history here. In the 1920s, when Alexander Friedmann and Georges Lemaitre were formulating these solutions, they didn't have supercomputers.
Right, they had chalkboards.
Exactly. And Einstein's field equations represent a system of 10 coupled, highly nonlinear partial differential equations.
10 of them.
Yes. Solving them exactly for a universe filled with billions of asymmetrical moving galaxies is literally impossible.
Right.
Even for today's most powerful computers.
So they had to simplify it just to get the math to work at all.
Precisely. They applied the cosmological principle to turn those 10 impossible equations into two relatively simple ones, the Friedmann equations.
Okay, so in mathematical terms, what they did is known as the averaging hypothesis, right?
Yes. They assume that the mathematical operation of averaging commutes with the operation of spatial evolution.
Meaning they assumed the difference between the average of the solution and the solution of the average was functionally zero on large scales.
Correct. We just swept the difference under the rug and said, it's close enough. We treated the deviations, the galaxies and voids, as tiny perturbations.
Like the ripples on the pond again.
Exactly. We assume we can plug a perfectly smooth, idealized stress-energy tensor into the nonlinear Einstein tensor and get an accurate representation of the macroscopic universe.
But here's where the problem becomes critical. If those ripples aren't just ripples, if they're actually tidal waves, massive superclusters, and vast voids where the density difference is huge, then that theory completely breaks down.
It does. Averaging stops being just a convenient, harmless math trick. It becomes a physical operation that actively alters observable reality.
Because by averaging the matter out before doing the math, you are literally erasing the gravitational effects of the structure itself.
Yes. The act of discarding that structural information actually changes the calculated geometry of the universe.
Wow.
If the universe remains persistently lumpy, the metric tensor and the Ricci curvature tensor respond nonlinearly to that lumpiness. The space inside a massive empty void expands differently than the space inside a dense galaxy cluster.
You can't just smear them together and pretend they act like a single fluid.
You really can't.
So if upcoming telescope observations prove that this permanent lumpiness is real, that the sponge never actually looks solid, what happens?
Well, our sources outline a literal cascade of failures.
It's like knocking over a line of dominoes that tears right through the standard model of cosmology. Let's talk about domino 1.
The first domino to fall would be the Friedmann equations themselves. As we discussed, these are the backbone of the Big Bang model. They dictate the expansion rate.
Assuming that smooth, uniform fluid.
Right. But if the universe doesn't smooth out, the Friedmann equations lose their uniqueness entirely.
Meaning there is no longer one single, simple story for how the universe expands.
Correct. In standard cosmology, the universe has a unique universal expansion history. It's characterized by a single scale factor, usually written mathematically as a gist of t.
So you can think of a T as the global clock of expansion. It tells you exactly how much the universe has stretched at any given moment.
Exactly. But if the universe is permanently lumpy, there is no single scale factor. Different regions will possess completely different effective expansion histories based on their local density.
Okay, so if we don't have a single scale factor, what happens to the Hubble constant? I mean, h0 is supposed to be the universal expansion rate today. Does it just cease to exist?
Well, it ceases to be a single number. Instead of a discrete value, h0 becomes p of h0, a probability distribution of regional expansion rates.
So it's like saying the universe isn't expanding like a perfectly uniform balloon being blown up.
Right.
It's expanding more like a bizarre, misshapen balloon where some patches of rubber are stretching incredibly fast and other patches are barely stretching at all.
Or even contracting locally. That is exactly what is happening in a lumpy universe. Voids, which are empty, expand faster.
Because there's no gravity holding them back.
Exactly. And dense galaxy clusters held together by gravity decouple from the expansion entirely. They don't stretch at all.
And that leads directly to the second falling domino, our observational probes. Every single tool we use to measure the cosmos relies on the assumption of a homogeneous background.
Every single one.
Let's talk about the cosmic microwave background, the CMB. For you listening, this is one of the most famous measurements in all of physics.
It's the afterglow radiation from roughly 380,000 years after the Big Bang, when the universe finally cooled enough for light to travel freely.
We look at tiny temperature fluctuations in this radiation map to understand the early universe. And there is a very famous feature in the CMB called the cold spot.
Yes, a large area that is unusually cool compared to the rest of the map.
Right. And in the standard model, that cold spot is usually interpreted as a primordial anomaly, like a literal imprint of some massive quantum fluctuation from the dawn of time.
That's the standard interpretation, yes.
But wait, let's let this breathe for a second.
Yeah.
If the universe is persistently lumpy, then that cold spot isn't a photograph of the Big Bang at all, is it? We are looking at the early universe through a dirty, lumpy windshield.
That is a brilliant way to phrase it. You are referring to something called the integrated Sachs-Wolf effect, or specifically the Rees-Sayama effect in nonlinear structures.
Okay, break that down for us.
Think about the photons coming from the CMB. They have been traveling for 13.8 billion years to reach your telescope.
Right.
They do not fly through a smooth vacuum. They have to fly through the cosmic web.
So what happens to a photon when it hits a giant void?
Well, when a CMB photon enters a massive empty void, it has to climb down into a shallow gravitational potential. As it does this, it gains a tiny bit of energy. It blue shifts.
Okay, so it gets a little energy boost.
But voids are expanding faster than the rest of the universe. So while the photon is flying across this massive void, the void itself gets significantly bigger and shallower.
Ah, I see.
When the photon finally climbs out the other side, the gravitational hill it has to climb up is smaller than the one it went down.
So it loses more energy climbing out than it gained going in. It becomes redshifted, it becomes colder.
Precisely. If there is a colossal 200 megaparsec wide underdense void sitting between us and the CMB in that specific direction, the void itself is warping the light as it travels to us.
It is actively creating the illusion of a cold spot on the map.
It has absolutely nothing to do with the primordial universe and everything to do with the lumpy foreground structure.
That is wild. It's an optical illusion generated by the cosmic architecture. And our sources say this lumpiness breaks our standard candles too, right? The supernovae.
Yes, it completely distorts how we read them.
We use type Ia supernovae to measure vast distances because we know exactly how chemically bright they should be. It is how we calculate the redshift distance relation.
Which is how we discovered dark energy in the first place, back in 1998.
Right. That discovery was entirely based on observing these distant supernovae and realizing they were dimmer and therefore farther away than the smooth model predicted.
But let's apply the lumpy universe model to this. What if the Milky Way galaxy, our entire local group, happens to sit inside a massive local underdense region?
A Hubble bubble.
Yes, a Hubble bubble.
Yeah.
If we live inside a massive local void, our redshift calculations are entirely warped.
Because the space around us is expanding faster than the global average. Because there is less mass holding it back locally.
Exactly. When we measure the redshift of galaxies moving away from us, we are measuring our own local accelerated outflow.
So we look out and think the entire universe is accelerating, but it might just be a localized distortion dictated by our cosmic zip code.
We are projecting our local weirdness onto the entire cosmos.
That is, that's just staggering. And it also distorts baryon acoustic oscillations, or BAO.
Yes, the BAO standard ruler.
Basically, these are fossilized sound waves from the plasma of the early universe that imprinted a specific scale on how galaxies cluster today. We use this ruler to measure how the universe has expanded over time.
But if the universe isn't a homogeneous background fluid, the geometry of space isn't uniform. The BAO scale would vary depending on which direction you look.
The ruler itself would warp, stretch, and bend based on the structural lumpiness of the specific regions you are measuring through.
You're trying to measure a curving, turbulent ocean with a straight-edged ruler that bends every time it hits a wave.
So what does this all mean for us? It means the foundational pillars of our understanding are shaking. If we don't have a homogeneous background, even the predictions of cosmic inflation become incredibly murky.
Very murky. Cosmic inflation is the theorized period of hyper-rapid expansion right after the Big Bang that supposedly ironed the universe out to make it smooth.
Right, but if the iron didn't actually smooth out the wrinkles, if the universe is still full of these massive fundamental structures, did inflation even happen the way we think it did?
That is exactly the profound question theoretical physicists are being forced to face right now. The observational data is putting immense pressure on the standard model.
And here is where the story pivots from merely tearing down old assumptions to building an entirely new, deeply elegant way of understanding reality. Because here's where it gets really interesting.
This is my favorite part.
What if dark energy, the mysterious, invisible, undetectable substance that supposedly makes up nearly 70% of our entire universe, isn't a physical substance at all? What if dark energy is just an illusion caused by bad math?
To explain this properly, we have to talk about back reaction. Specifically, a concept known in the literature as kinematical back reaction.
Okay, let's get into it.
Remember how we discussed that the Einstein field equations are highly nonlinear, and that mathematically averaging the matter before solving the equations alters the geometric result?
Right, sweeping the structure under the rug changes the shape of the room.
Exactly. Well, theoretical physicists, most notably Thomas Buchert, have developed a rigorous set of equations, the Buchert formalism, that actually accounts for this nonlinear averaging.
So they did the hard math.
They did. And when you properly average the nonlinear equations over a genuinely lumpy and homogeneous domain, you generate extra mathematical terms that do not exist in the perfectly smooth equations.
Extra terms, like what?
Well, one of these critical extra terms is called QD, the kinematical back reaction term.
Okay, so what exactly is QD capturing in the real world?
It mathematically accounts for two things. First, the variance in the expansion rate across different regions, the fact that voids expand fast and clusters don't expand at all.
Makes sense. And the second thing?
Second, it accounts for the small-scale shear. Shear is the twisting, tidal stretching, and deformation of matter as it falls into these complex cosmic web structures.
Okay, so QD is basically the mathematical receipt for the lumpiness. It is the leftovers from the nonlinearity of the gravity field itself.
That is a brilliant way to conceptualize it. Now, in the standard, perfectly smooth lambda CDM cosmology, QD is strictly assumed to be zero.
Because there is no variance and no shear in a perfectly smooth fluid.
Exactly, so there is no back reaction. But if the universe remains lumpy, QD does not equal zero. It becomes a dynamically active scalar field in the equations.
And here's the absolute revelation for you listening. The mathematical effects of this QD term behave exactly like dark energy. It mimics a repulsive, accelerating expansion perfectly.
It is uncanny how perfectly it mimics it.
That is mind-blowing. So the observed acceleration of the universe is real. The supernovae really are moving away from us faster than a purely matter-filled model predicts. But the ontology changes completely.
Precisely. Instead of having to invent a magical new energy component that violates the strong energy condition to explain it, the acceleration naturally emerges from the statistical geometry of the cosmic structure itself.
Dark energy transforms from a mysterious physical thing into a macroscopic mathematical artifact. It is an emergent phenomenon created by the structural friction of the universe.
And this ties directly into one of the most rigorously developed alternative models in our sources, timescape cosmology.
Timescape cosmology, I love that name.
It's pioneered by physicist David Wiltshire, and it provides a definitive physical mechanism for exactly how this optical illusion of acceleration is sustained. And it relies purely on the proven laws of general relativity.
No magical new particles needed.
None. It revolves around a concept you are likely familiar with: gravitational time dilation.
Okay, I know that clocks tick slower in a gravity well. General relativity tells us that time is relative and proximity to mass slows time down. But walk me through the exact path of the light here. I want to track the photon.
All right, let's trace the photon step by step. As you said, general relativity dictates that clocks run at different speeds depending on the depth of the gravitational potential well they are sitting in.
Okay.
Now, look at our lumpy universe. You have incredibly dense walls and filaments packed with thousands of galaxies, and you have these vast, expanding, empty voids.
The gravitational potential in a dense wall is very deep.
Right. And the potential in a void is extremely shallow. Because of this, a clock floating in the middle of a massive, empty void ticks relatively fast compared to a clock sitting in a dense galaxy wall.
And we, human beings on Earth, in the solar system, inside the Milky Way galaxy, we live deep inside a bound, dense structural wall. Our clock is slow.
We do. We are deep inside a gravitational well. Now imagine a supernova detonates in or near one of these vast voids.
Okay, the photon is emitted.
It travels across billions of light years of expanding space, mostly traversing these fast-ticking, rapidly expanding, empty voids.
Just flying through the fast time zone.
Exactly. Finally, the photon falls into our dense galaxy cluster, down into our gravity well, and hits your telescope.
Okay, the photon has arrived. Why does it look like dark energy is pushing it?
Because of how we define expansion. We measure the expansion of the universe using our local clocks and our local rulers. Timescape cosmology suggests that we are fundamentally misinterpreting the data because we are comparing the light emitted from these fast-ticking voids using our slow-ticking local clocks.
The observer's location matters. We are not some hypothetical volume-averaged observer sitting completely outside the universe. We are embedded in the structure.
Because our local time is dilated relative to the volume average time of the voids, our measurements of the light's redshift and luminosity distance are totally skewed.
The expansion appears to be accelerating because our clock is ticking slower than the clock of the space the light traveled through. It is a massive trick of perspective, an optical illusion born from general relativistic time dilation between different cosmic densities. There is no lambda. There is no dark energy field permeating space. It is just the warped nature of time and space playing a trick on our telescopes.
It is a profound, radical, yet completely mathematically grounded alternative. It solves the dark energy problem without needing any new physics beyond what Einstein gave us in 1915.
That is just incredibly satisfying.
And we might actually be seeing the first physical cracks in the current standard model right now, playing out in real time in the astronomical data.
Yes. You were talking about the Hubble tension. This isn't just theoretical musing. This is a massive, highly contentious drama unfolding in the astrophysics community right now.
It really is the biggest crisis in modern astronomy.
For years, scientists have been measuring the expansion rate of the universe, and the two main methods are giving violently different answers.
If we measure the Hubble constant by looking at the early universe, using the Planck satellite to measure the cosmic microwave background, we get a Hubble constant of 67.4 kilometers per second per megaparsec.
But if we measure it by looking at the late modern universe, using the SH-ES team's measurements of local Cepheid variable stars and supernovae, we get a value of 73.0.
And these aren't just minor rounding errors. These are highly precise, rigorously checked measurements.
Exactly. The statistical disagreement between these two numbers is now between 4 and 5 sigma. In physics, a 5 sigma discrepancy means there is roughly a 1 in 3.5 million chance that the difference is a statistical fluke.
And for years, the two camps of scientists have been arguing bitterly, publishing papers accusing the other side of systemic measurement errors, miscalibration, or essentially having broken telescopes.
But what our sources suggest is that this 5 sigma disagreement isn't an error at all. Neither telescope is broken. The Hubble tension is the very first definitive observational clue of cosmic variance.
That's the theory, yes.
The early universe measurement of 67.4 is the global volume averaged H0. But the local measurement of 73.0 is our specific local H0 because we live in a lumpy, underdense region that is expanding slightly faster.
Both measurements are entirely correct. They're just measuring different domains of a lumpy universe.
If we connect this to the bigger picture, the question becomes, how does the scientific community actually handle this realization? You are talking about overturning a century of assumed cosmology.
It won't be easy. Our sources lay out a very pragmatic, structural, four-phase roadmap for a 10 to 20-year paradigm shift. Because this kind of change doesn't happen overnight, it requires overcoming massive institutional inertia.
Let's walk through that roadmap. Phase 1, roughly years 1 to 3, is crisis validation. This is where the massive surveys like Euclid and the Square Kilometre Array actually deliver the definitive proof.
They hit that gold standard 5 sigma p-value to firmly announce that the FLRW metric is insufficient, that the smooth universe assumption is demonstrably broken at all scales.
That would be an announcement on par with the 1998 discovery of the accelerating universe.
Yes, but the real friction begins in phase 2, roughly years 3 to 7. The sources call this theoretical retooling. And you have to understand the human element here.
Oh, the academic drama.
Exactly.
Yeah.
This is where the hard, painful mathematical work happens. You have tenured professors who have spent 30 years publishing papers based on lambda CDM who now have to accept that their foundational metric is flawed.
Graduate textbooks literally have to be rewritten. The Bouchard averaged equations, complete with the back reaction terms, must move from being considered fringe theory to becoming the standard curriculum.
We have to stop using a single Hubble constant entirely and start teaching domain-dependent parameterizations.
The Hubble tension is officially reclassified from an embarrassing systemic error to a fundamental expected feature of the lumpy universe. It gets messy.
It gets very messy. And then, once the theory is updated, we move to phase 3, years 5 to 10, observational reanalysis.
So we have to go back and completely rebuild the cosmic distance ladder without assuming a smooth background.
Yes. Our sources heavily emphasize using something called the kinetic Sunyaev-Zeldovich effect, or the KSZ effect, to do this.
How exactly does that work? How do we map the universe without standard candles?
Well, the KSZ effect is a brilliant observational tool. It relies on the interaction between the cosmic microwave background and the hot gas residing inside massive galaxy clusters.
Okay.
When CB photons travel through a galaxy collector, they interact with the free electrons in the hot ionized intracluster gas. This is called Thomson scattering.
Got it.
Now, if that massive galaxy cluster is moving relative to the cosmic background, if it has a bulk velocity, the scattered CMB photons receive a tiny Doppler shift. They get slightly blue shifted or red shifted, depending on whether the cluster is moving toward us or away from us.
So by measuring these tiny temperature shifts in the CMB around specific galaxy clusters, cosmologists can actually trace the exact speed and direction those clusters are moving.
Exactly. They can measure the bulk, peculiar velocities of enormous structures. In this phase 3 roadmap, observational cosmologists would use the KSZ effect, alongside redshift space distortions, to build an actual three-dimensional map of the velocity field of the universe.
They aren't just mapping where the matter is located, they are mapping exactly how fast different pockets of space are expanding and contracting.
Which allows us to empirically measure the variance and the exact components of the QD back reaction term.
That is incredible. A true 3D map of the expansion rate itself, proving the variance dynamically. And finally, we reach phase 4, years 10 to 20, new consensus.
The community finally stops fighting and officially adopts a new standard model.
The sources suggest two likely candidates emerge from the ashes of Lambda CDM. One is Lambda CDMB, which is basically the old model, but with a specific back reaction parameter mathematically patched in to account for the lumpiness. It is the conservative approach.
The other candidate is the more radical timescape model, where dark energy is discarded entirely, lambda is set to 0, and the observed acceleration is purely understood as an apparent effect of gravitational averaging and time dilation.
Which model wins will depend entirely on the data gathered in phase 3.
Exactly.
And this brings us to the profound pedagogical shift that this entire revolution requires. We are talking about fundamentally altering how we perceive physical reality. We are moving from a universe defined by exact, rigid homogeneity to one defined by statistical, emergent homogeneity.
Which means we have to completely change the analogies and the conceptual frameworks we use to teach this to the next generation. The universe stops being a perfectly smooth, expanding rubber balloon.
That analogy has to die.
It really does. The universe becomes a turbulent fluid.
Yeah.
I really appreciate the idea from the sources that future textbooks might literally require a historical warning box printed in the introductory chapters.
Oh, like reading, did 20th century physicists mistake the structural roughness of the universe for a new form of energy?
Exactly. It's a very humbling thought.
It really is. And this raises an important question, perhaps the deepest theoretical concept we've touched on today, the information theoretic interpretation of the universe.
Yes. In standard cosmology, by replacing the actual lumpy, complex matter distribution with the smooth theoretical average, we are actively discarding structural information.
We throw away the data about where the voids in the clusters are.
But in a nonlinear theory of gravity like general relativity, that discarded information has immense physical weight. It has dynamical consequences. The geometry of space-time retains the memory of that structure.
So it's not just about how much stuff is in the universe, it's heavily dependent on how that stuff is arranged. The geometry depends on the architecture.
Exactly. This is the crux of the information theoretic view. Geometry depends not just on the absolute amount of mass energy, but on the organization of that mass energy.
Okay, wrap your head around this. If you have two hypothetical universes with the exact same total amount of mass, they can have entirely different large-scale dynamics.
Different expansion histories, different apparent acceleration rates.
Just because one is organized into incredibly tight clusters with massive voids, and the other is organized like a perfectly smooth fluid.
It's fascinating.
It makes me think about thermodynamics. It's like the emergence of entropy. If you have a box of gas, the macro state, the temperature and pressure of the box, is entirely dictated by the specific organization and movement of the microstates. You know, the billions of atoms bouncing around inside. You can't just ignore the atoms.
That is a perfect parallel. This paradigm shift represents a massive maturation of cosmological physics. It is directly akin to the historical realization in the 19th century that heat isn't an invisible fluid called caloric that flows between objects, but rather the statistical emergent property of atomic motion.
Oh, wow.
For the past century, we have treated the expansion of the universe like caloric fluid. We now have to treat it like statistical mechanics. The organization of the cosmic microstates, the voids and walls, dictates the macro state of the expanding universe.
And we have to grapple with what this means for the Copernican principle, right? That is the long-held philosophical bedrock of astronomy. The idea that humanity does not occupy a special, privileged, or central place in the universe.
Right.
If our local measurements are warped by our specific location in a galaxy wall, does that mean we are special?
That is a crucial point and a frequent misunderstanding. We do not have to abandon the Copernican principle. We aren't in the center of the universe. We aren't in a uniquely special place.
Okay, that's a relief.
But we must mature our understanding of the principle. For decades, the Copernican principle has been lazily conflated with exact homogeneity, the idea that everywhere is exactly the same as everywhere else.
Right, which we now know isn't true.
We must shift to realizing that the universe is statistically uniform only after incredibly complex averaging over time and vast light cones. We are not in a privileged place, but we are embedded in a specific local geometry, and our physics must account for that local environment.
It is a much more nuanced, sophisticated way of viewing our place in the cosmos. Okay, let's bring this all together. What an absolute journey.
It really is.
If the universe refuses to smooth out, if it remains persistently, stubbornly lumpy on the grandest scales imaginable, it doesn't break Einstein's general relativity. In fact, it proves just how beautifully, terrifyingly complex general relativity truly is.
Absolutely.
It proves that cosmic structure, the vast, sprawling web of voids and filaments, is fundamental to reality itself. It is not just a decorative afterthought sprinkled on top of a smooth, expanding background space.
Well said.
Our job as a scientifically literate species isn't just to ask what the underlying geometry of the universe is, but to understand how the cosmic structure actually generates that geometry.
And for you listening to this, the ultimate takeaway is that the smooth universe was always just a convenient mathematical fiction. It was an approximation, a scaffold that allowed us to make sense of the cosmos in the 20th century before we had the observational power to see the truth.
But the real universe is beautifully chaotic and persistently lumpy.
And learning how to mathematically and observationally average that extreme lumpiness without losing the truth of it is undeniably the next century's greatest challenge in physics. It is not a crisis. It is a profound evolution of our understanding.
Which leaves me with one final, deeply provocative thought for you to mull over today. We've spent this entire time talking about how the most dominant force in our universe, dark energy, something supposedly making up 70% of reality, a force determining the ultimate fate of the cosmos, might turn out to be nothing more than a statistical mirage.
An optical illusion born from the complex arrangement of matter and our own mathematical inability to properly model the true lumpy shape of the map.
Exactly. If something that massive, something taught as absolute physical truth, can be a mere trick of perspective. Wait, let me rephrase that. If it can be just a trick of perspective, what other fundamental truths or invisible forces in our daily human reality are just illusions, created entirely by our inability to perceive the deeper, lumpy structure of the world around us? Think about that the next time you look up at the night sky. Thanks for taking the deep dive with us.